Day 3, AP Physics. Problem starting on page 85. This problem actually is on page 86. Problem number 13, we are referring back to this diagram from page 61. There's kind of two graphs in one here. The solid line, which I've already got marked off with a red dot, I've got a red dot right there, which is roughly at about 3.8 seconds, almost 4 seconds. It's the best I can do. I can't get real accurate with this pen. That's what we're talking about that time. We have an instantaneous speed at that time of about 7 miles per hour, and the car is increasing in speed from a speed of 0. Once again, we're assuming going in a straight line, not turning. This dashed line represents how far the car has gone over time. You would read this scale. We're not reading this scale over here on this side right now, so we have a dual function graph here, two graphs in one. The time is the same for both graphs in seconds, but the speed is in miles per hour, and we're at this spot right here. So the speed's increasing, but we're looking for the acceleration. This is the approximate acceleration at that time. So they're asking me for the instantaneous acceleration at that time. Now for the first, like from this spot to about here, the acceleration looks like it's pretty straight. It's curving a little bit, and I can't really draw tangents on here too well. So you would have to draw a tangent line, but I'm still going to say, okay, from here to about 5 seconds, it's pretty straight, and that's a good amount of time. So once again, there really is pretty much an average acceleration, or an average acceleration that's constant. So it's pretty much a uniform acceleration for the first 5 seconds. Technically, well, it's getting less, and there's less and less of an acceleration later on because the graph starts to flatten out. There's less and less acceleration. But if I just look at the equation once again, that the average acceleration, that's average acceleration equals delta V over t. And we could get an average acceleration for 30 seconds, or well, probably not 30 seconds because it doesn't go to 30 seconds, but for 20 seconds, the average acceleration would be a little bit less than what we're going to get now, because the most acceleration is like during the first 5, 6, 7 seconds. It's pretty uniform. I'm going to say it's pretty much a straight line from 0 to 5. If I were to draw a tangent, it would go right on top of that line, that graph, pretty linear, and you can look at it pretty closely, but I'll be real close with, that should say AVE. I'm not sure why. Okay, AVE, the average acceleration. The delta V for the first 5 seconds, it's about 35, it increases about 35 miles per hour now in that 5 seconds. So you would say the average acceleration, not AVE, the average acceleration is about 7 miles per hour per second. That would be the units, and you could convert that into meters per second squared, but we don't have to right now. That's our average acceleration, gaining about 7 miles per hour per second, roughly for the first 5 or 6 seconds, and then it starts to lessen the acceleration, but still increases the speed after that.